The object of this experiment is to demonstrate Newton's first law, which states that an object in motion tends to stay in motion at constant velocity unless acted on by an outside force. For this experiment, I chose to use a golf ball because of its smooth surface and known mass, and it's what was available to me. I rolled it across a known length, in this case an 8.5 by 11 sheet of paper. I took the 11 inches and converted it to meters, which was 0.2794 meters. I set the origin for my data points with the origin at the center of the ball, negative x-axis on the left, negative y-axis on the bottom, and vice versa for the positive. I recorded the position over regular intervals, took my first two data points, and used those to calculate the initial velocity, which in this case came out to be 0.309 meters per second in the negative x direction. I now have all the initial data needed in order to try to predict what the overall ball motion will be over a set period of time. So I used the program given to us, set the ball's initial mass to 0.04593 kilograms, the initial position to the vector 0, 0, 0, which is straight off the tracker program, the ball velocity to what we calculated through Excel, which is 0.3089 meters per second in the negative x direction. The time between each execution of the program is going to be 0.033 seconds, which is the refresh rate of the camera, and the overall time period to 1.33 seconds. Also double check that the equations are correct for Newton's second law, which is ball velocity final equals ball velocity initial plus the overall force divided by ball mass times the change in time, and that the ball position final, or for each iteration, is going to be the ball position initial plus the ball velocity times the change in time. I can now run the simulation after removing the appropriate hashtags, making sure that it'll export all the data points to an external Excel file. And plotting these versus the data points of the observational data yields this graph, which, as you can see, the orange line, which is my prediction, is not quite the same as the blue points, which are the observational data. At first I thought this might be due to the fact that we used the first 2 points in order to calculate the initial velocity of the ball, and that those first 2 points are based on trying to find the center of the ball, which is kind of hard to do on a blurry object to find the exact center, and that error, if there was any, would be projected throughout the entire predictive model. So in order to try to minimize this, I used my first point to calculate the speed as the origin, and then the second point somewhere in the middle of my experimental data, which was right about here. And what that gave me was this yellow line for my new predicted position. And as you can see, it's more accurate, but not quite as accurate as I'd like it to be. And another thing you'll notice is that this is the point that I used to calculate the average velocity, and that the points before it are below the line, the points after it are above, which shows that this experimental data is actually curved, which shows that there's probably a net force acting on the object. Otherwise, it would be in a straight line indicating constant velocity. Now, this force can be anything due to the dimples in the golf ball, slowing it down to drag, or even gravity, since I can't tell whether or not the ground is level. So even though I can't tell what the force is, I can say what the magnitude of the force is. And to do this, I use the first 2 points of my experimental data to find the velocity initial, the last 2 points to find the velocity final, and the overall time period as delta t. Took the mass of the ball, plugged it into Newton's second law equation after manipulating it to look like this, and got an F net, force net, equal to this number, which I'll show you after I plugged it into my final predictions. I modified the F net vector by plugging in my Excel calculation, reran the simulation, and that is how I got my final lab results, which, as you can see, they pretty closely align in this case, and even though they're not perfect, they're pretty close. if I had started this experiment deciding to make this side the positive x-axis, this side the negative, it would have made the graph look different. It would have flipped this over this 0 line and made it look like the mirror image of it, which would have made it look different, but in effect, the distance between these two would be the same, which, for our purposes, would be no difference. Now, as for the total net force is equal to 0, in this case they didn't. But if they did like they should, it's possible to say what added up to that, because it should be no net forces, and therefore no forces acting on the ball whatsoever. So 0 forces acting on the ball equals a net force of 0.